Yes. Perfect. We just check on this works. Okay. So thank you very much to the organizers, first of all, for bringing this conference to Bulgaria, and second of all, for giving me the opportunity to represent the small bodies community. And the reason why I'm starting with this slide is because today we have a great reminder that we're part of the solar system, and that is a solar eclipse, a partial solar eclipse, which is starting about 30 minutes from now. So at the end of my talk. And I conveniently have brought a few pairs of glasses that will allow us to safely look at it. So if anyone's interested, please come and talk to me after the talk and we'll go out and look at the sun. So the partial eclipse is about 30%, and with the glasses we'll be able to see it. The other reason why I start with this slide is because the solar system is just so much more fascinating when we look at it and add the small body populations. And hopefully by the end of the talk I will convince you of this, and I will plant the seed in your mind that when we're thinking about habitability, when we're thinking about exoplanetary systems, potential life and so on, we should give small bodies a thought and what their influence in such systems are. And I will start up front with a bit of a disclaimer. So the small body research relies on four main methods, let's say. So we rely on telescopic observations, we rely on in situ spacecraft studies, and also on laboratory work, modeling, and theoretical work. And my research so far has focused on telescope observations mainly, and also on spacecraft, and that's why this presentation will be slightly skewed in this direction, so that's my personal bias. And on the other hand, I've tried to include points to consider, which would be hopefully interesting for many people in the audience, and that's why I've tried to make the talk broad and focusing on just a few examples to show the power of small body research. Talking about small bodies, for the broad audience coming from many disciplines, I'd start by saying that we're talking about mainly asteroids and comets in the solar system. The asteroids are mainly concentrated in the main asteroid belt between Mars and Jupiter, and also there are some asteroids in the near-Earth space, so closer to the Earth. And in the outer solar system we have other major populations, so that is the Kuiper belt or the trans-Neptunian region, where we have a donut-shaped structure of thousands of objects beyond the orbit of Neptune, and also it extends from between 1,000 up to 100,000 astronomical units from the Sun, where we have the Oort cloud, which is the sort of population of the long-period comets, which we'll talk about. And comets are the objects which come close to the Sun and are volatile, so they have ices, which get heated close to the Sun, which forms their tails. But comets start with having a nucleus, so when we look at a comet and an asteroid, they both look rocky, but comets hide much more volatile content, much more ices. And the distinction traditionally in the literature and in the field has been that asteroids are planetesimals, which are formed closer to the Sun, so they don't have any ices left in them, while comets source from this population, which is formed at higher heliocentric distances, and therefore they have ices in them. And the other thing about small bodies, it was mentioned in the talks this morning, is that they preserve the properties, some of the properties of the planetesimals, so they're our direct witnesses of planet formation, and they provide rich information that can constrain a lot of what we're interested in. And for the sake of this talk, I've divided the information that we can get from small bodies in 4 different areas. And I'll go in this order because it made sense for the presentation. This is not necessarily the order of importance. So small bodies give us evidence for all stages of the solar system evolution because they were formed early on and then they kept on evolving and they keep on evolving nowadays. Another point that I want to highlight is specifically about the planet formation epoch and what properties these planetesimals preserved to this day and what we can use them to derive about the planet formation mechanisms that we're interested in. We are also discussing, so this morning there was a lot mentioned about the delivery of important materials to the planet, and in particular to the Earth, because that's where we have life. And if we're talking about habitability, it's important to know whether comets and asteroids deliver important materials, be it minerals, be it ices, or even organic molecules, which are prebiotic molecules. And finally, the last point I'd like to make is, what about small bodies' potential of destroying life? And I will briefly touch this topic because it's fascinating to think about not only how the bodies in the solar system helped us create life, but what can they do to Earth and what can they do to other planets, which potentially develop life. So let's start with the first point. And the first point is about the fact that small bodies bear the evidence of many important epochs in the solar system evolution. And in particular, I'll focus on planet migration, because it is constrained by the populations of small bodies that we observe nowadays. So the planet migration scenarios were motivated by many different observables in the solar system, also in exoplanetary systems. The interesting thing is that looking deeply into the structures that we observe, so the populations of small bodies in the solar system, we actually can fine-tune the models which are being run to understand them better. And the first planet migration type that I pointed out on this slide is the so-called grand tack. For the non-experts, we don't need to go into the specifics of what this model is, but this is planet migration while there is still gas in the disk. And what happened is Jupiter and Saturn migrated inwards, then they stopped because of the coupling that they entered, and we ended up with them moving outwards, and the structures that were left over in the solar system can still be observed, for example, in the main asteroid belt, where inwards we have the S-type asteroids. You can see my pointer. And these are the rocket-type asteroids, and then the more volatile-rich or carbon-rich asteroid types are in the outer main belt. So this is one piece of evidence that we observe in confirmation of this planetary migration hypothesis. The other planetary migration epoch that we focus on a lot in solar system research is the so-called NEAS model. So that's the planet migration which happened when the gas has dissipated and we have the planet surrounded by planetesimals. So these planetesimals, which didn't make it in the contents of the planet, in the planets, they started interacting with the giant planets, which is a very interesting hypothetical process. So there are many evidence pointing to it happening, but we should still remember that it's a model. Led to the migration of the giant planets outwards, except for Jupiter, and structured the solar system in ways that we can very well see, especially in the outer solar system. So the simplest thing that happened is that there was this red population, so these are the so-called cold classical Kuiper belt objects. They were formed where they are observed now. So this is in the very outer solar system, while other objects were formed closer to the Sun, but they were emplaced by this planet migration. And this can be seen well in the structure of the Kuiper belt, where we have the dynamically hot population and we have the cold classical objects. And here I want to highlight one space mission which provided a lot of information regarding this, and this is New Horizons, which first visited Pluto and its system and then continued in the Kuiper belt and gave us a very deep analysis of one of these very primordial objects which was formed where it's found today, and it has experienced very little evolution throughout the history of the solar system. So this is very valuable information. On the other hand, the NIS model was predicting that many of the planetesimals, in fact most of them, which were in the transplanetary disk, originally formed beyond the giant planets, were ejected from the solar system. And for years, people were saying that if objects were ejected from the solar system, then other systems should eject their planetesimals, and there will be the so-called interstellar objects. And indeed, in 2017, the first one appeared, and we detect, so many have appeared throughout history. It's the first one that we have detected, so that was Oumuamua. And very soon after, a second one was detected, that is 2I Orso. So a new class of objects in the small bodies in the solar system was defined the interstellar object. And that is a direct link between the studies of what we learned in the solar system and what can be found out about other systems in our galaxy, because these objects are visitors from objects which have, from systems which have experienced potentially different evolution, different formation scenarios, and they come right up to us and provide us opportunities to study. So another point of the evolution of the small bodies, it's actually something that I want to pay attention to because that's the area where I work on. And this is what happens to the short period comets that we studied in the current epoch. So the NIS model tells us that these objects were formed beyond the giant planets, then they were placed onto the Kuiper belt, where they have spent the last few billion years undisturbed and are mostly unevolved there. So they're frozen capsules, as people in cometary science like to call them, which come closer to the sun through some migration that's happening in the current epoch. So most orbits are stable in the Kuiper belt, but very few of them interact with Neptune and progressively with the other planets and come closer to the sun and end up being short period comets. And short period comets are very convenient, so this is the mechanism. So from the Kuiper belt we go through the Centaur phase, which is when activity starts, and then they become the so-called short period comets. And they're short period because their orbital periods are around 20 years, and they're amazing because we have the opportunity to study them more than once. So long period comets, they come close to the sun once in our lifetime, and then they're gone. While short period comets, we observe them again and again, which allows us to send spacecraft easily to them and to ask deeper questions about comet formation and evolution. And because of their proximity and easily being accessible to spacecraft, we have studied a number of them. So we have actually imaged the surfaces of these comets here, and these are direct images from in situ spacecraft. And the latest one was the Rosita mission. So there are very few people on the planet probably who are interested in to look in space that haven't heard about the Rosita mission. But the Rosita is spectacular because for the first time we managed to observe the comet evolve in front of our eyes, because the spacecraft accompanied the comet for 2 years along its perihelion passage. And I'm paying attention to this mission because it's provided some of the most fascinating results from the past years, and I'll mention them later. But there is something else that I want to highlight. So as I told you, this evolution of short period comets is not very straightforward in terms of they haven't been frozen and now they just come. But they go through activity phases before they become Jupiter family comets, then they evolve along their orbit. So they're not quite pristine. And if we want to look at an object which has spent billions of years away from the sun and hasn't been processed, we need to look at dynamically new comets, so objects which are coming from the Oort cloud for the first time, because they will be unaltered. And luckily, we've developed a mission called Comet Interceptor, which has been adopted by ESA this year, which will allow us to park a spacecraft in L2 and then go and visit the comet, which we haven't discovered yet. So we will discover it in the next few years. We'll make sure that it's coming close to the sun for the first time, and we'll send a spacecraft to it. The other option is very unlikely statistically, but it's still possible that if there's a suitable interstellar object, we can also send Comet Interceptor there, and that will be spectacular to compare to a different system around a different star. So that brings me to the next point, constraining planet formation. So we've heard a bit this week about the different planet formation scenarios, and the interesting thing is that if we keep in mind all the caveats, we can in first approximation say that comets are the objects which have been altered the least, and we can study them in order to understand how they were formed because they haven't been changed that much. And even more so, this would be true for other objects out there in the solar system, so I'll go back to our growth in a minute, but first, what do comets tell us? And I told you earlier that space missions, in situ space missions, allow us to send laboratories to these objects, and we can have very detailed analysis. And this is a result that I used as an example, which is from MIDAS on Rosita, which detected fractal-like structures on some of the fluffy particles, fluffy dust particles that they detected in the coma of 67P. And it is pointing to the conclusion that these fluffy particles evidence for streaming instability formation rather than having core accretion, for example, happening in the outer solar system. As I said, it's even more interesting when we look at the outer solar system. So this is Arrokoth, which was visited by New Horizons, and it has a very, very peculiar shape. And this shape is very interesting to model, and the models are showing that these two objects formed separately in the same cloud of material, and they slowly came together in a very non-violent impact, so in a very gentle impact. And the formation and the observations leading to the formation scenario tell us again that we're talking about a cloud collapse of pebbles happening in the streaming instability that has formed these objects. So direct evidence for processes which can help us constrain the formation scenarios that we're talking about. And I've just thrown this in here because we can study objects also from the ground. So this is the light curve, the rotational light curve of a binary object. So we don't have to send spacecraft to find out everything about small bodies. We can study them from the ground very efficiently, and building the statistics on binaries, for example, in the Kuiper Belt, also helps us further constrain how they were formed. So this is the third point. This is the delivery of potentially building blocks for life on Earth. And I'm not going to go in a lot of detail here, but different cometary groups. So I'll put it this way. So one of the main motivations for some of the recent cometary missions has been to measure the D2H, so the deuterium to hydrogen ratio, in comets, because it was suspected that it's similar to the D2H ratio of the oceans on Earth, and which suggests that comets have delivered the water which formed the oceans on Earth. Rosita challenged this because the D2H ratio of 67P is different, which strangely is not showing on this plot, but 67P differs from the other comets, which made people go back and say, okay, so maybe comets are not the biggest contributor to this D2H ratio. Asteroids match, and also here is the point to mention that the classical distinction between asteroids and comets is no longer so classical, and we believe that asteroids, or especially those formed further away from the Sun, also have water content which could have been delivered to the Earth. Another beautiful slide taken from the Rosina team on Rosetta is their library of molecules which they detected in the coma of the comet. And they have built a so-called Rosina Zoo, the Rosetta Zoo. And these are some molecules which are very useful for forming life, and many people in the audience can talk about this much more confidently than I. But I'm just pointing this out to say that space missions to small bodies have the potential to give us direct evidence that is useful for us to develop the models of what was possibly delivered to the Earth that could have led to enriching the material that could be used for forming life. And the other point that I want to make while we're talking about the composition of comets is that there is a direct link between the composition measured of comets and that of protoplanetary disks measured in other systems, so in telescope observations of planet-forming regions. And this direct link allows us to think about how universal it is that our planetesimals contain certain compositions. It allows us to think about whether other systems can be different and so on. And comets are very useful for this because we can now have very sensitive measurements of their compositions, both from the ground using sub-millimeter observations especially, and also by sending spacecraft to them. So the final point here is that I've called it hazards to life, but it might also be not so dark. And it's good to be cautious with comets because traditionally in history people have been afraid of them, very afraid of them. And these are some of the images that I find amazing from 1910 when the Halley comet had an approach. And people use this to sell all kinds of strange products to make use of people's fear that comets are going to contaminate Earth and eradicate life. So they sold comet umbrellas and anti-comet pills. So I wouldn't like us to be that afraid of comets, but it's still important to think about how life on Earth relates to what's happening in the surroundings of our planet. And this, from the historical records that I've heard from people, was that planetary defense wasn't taken very seriously until the impact of Comet Shoemaker-Levy on Jupiter. So that's when a comet was observed to disintegrate and impact Jupiter. And after that, after people really saw that planets interact with comets, planetary defense really picked up. So since then, effort has been made to map all the possible asteroids, and this is a continuous effort that will continue over the next decade and beyond, to really know what's in our surroundings and what asteroids mainly can impact us. And asteroids are more likely to impact us than comets. But the point here is that this can really, in the current epoch, pose small dangers to certain habitats, to certain cities, for example, because statistically the impacts will happen from very small asteroids, but it's not excluded that a large one is heading our way, and we should be prepared for it. A more extreme scenario that's being considered, but that's not in our lifetime, is what would happen if there is a close passage by a star which perturbs the orbits in the Oort cloud and sends objects from the inner Oort cloud on the so-called comet showers that just bring a lot of comets to the inner solar system and they impact the planets. And this is the scenario I wanted to end here with, because that's something to consider for other systems we're looking at. Because other systems might have their Oort cloud equivalents, and they might have their close passages by stars. So it's interesting to consider to what extent such comet showers, intensive showers of comets, could influence either the formation of life by enriching the planet or the extinction of life. So here is the outlook, because I couldn't talk a lot about specific observations and specific space missions. So I wanted to highlight a few of them. And in terms of laboratory work, it goes into directions. One direction is trying to simulate for example, cometary or asteroid materials and their formation, also their evolution, but also sample returns. So we've had sample returns from 2 asteroids and also from 1 comet, from stardust. So these are going to generate results in the next years, profound results. In terms of space missions, we have had DART and Hera is going to go back to the same asteroid that DART impacted a few weeks ago. So we will learn a lot about asteroids in the inner solar system. There is Psyche, which is going to visit an iron-rich asteroid. So hopefully that will give us information if this asteroid ends up being material from an iron core. Then there is Lucy, which is going to visit the Jupiter Trojans. I don't have time to go in detail, but that's going to be fundamental. So keep your eyes open to this mission. And we heard about New Horizons. So New Horizons will possibly have an extension if they find a target, and will have Comet Interceptor, as I mentioned. In terms of ground observations, we can use almost any telescope you can think of, especially those in the visible, UV, and infrared. And we will continue doing so there will be a lot of discoveries. A fundamental change will come once we have LSST, because LSST is a survey telescope that will map and allow us to discover a lot more small bodies in the solar system, characterize them, and understand, map the populations and understand them better, which is going to bring a lot of, hopefully, interesting change in the field. And also JWST is opening lots of opportunities for studying small bodies and understanding them better, and in the future we'll have the ELTs contributing to this. So here is the summary slides. These are the 4 aspects of how small bodies can inform the topics we're interested in this conference. And I'll leave you with this slide and the reminder that we can go watch the solar eclipse at some point, before or after lunch. Thank you.
Hi, thanks a lot for that great presentation. It reminds me the time when I observed neowise. It was a few years ago. My name is Petr Evtimov, Sofia University. So I would like to bring you back to that last topic of your presentation, which is about hazards to life. And as I heard, about 70,000 years ago from now, a star has passed nearby solar system. It's called Shoal Star. And in less than 2 million years from now, we will witness the consequences of that passage. So, no pressure, but what will happen to all of us?
I think that all of these studies, so I'm not familiar with this one in particular, but my general understanding of the field is that it really depends on the population in the inner Oort cloud, how dense it is. So the work that colleagues are doing is they start with a certain population that we assume, they model the passage of the star, and they see how many planetesimals will be sent to the inner solar system. So if we have a very densely populated inner Oort cloud, we'll be in a bit of trouble in a few million years. Also, Gaia is enabling this. So Gaia is a satellite that mapped the proper motion of a lot of stars. So it's allowed people to study the solar system vicinity and to see which other potential stars could at some point lead to this. But to my understanding, it depends on the Oort cloud population, which is very difficult to model and so far impossible to observe. So there's some efforts to detect objects and build some statistics, but these should be long-term projects because we cannot directly image them. We rely on building statistics when they're them passing in front of stars. So I wouldn't be concerned at this point from what I've seen, and it's also not going to be our lifetime, and we have other hazards to think about now, but it's an interesting area.
We have other questions? Okay, well, let's. Is there one? Oh, okay. Well, I'm going to worry about it anyway, even if it's taking a long time.
Thank you for the very interesting talk. I was really excited to hear about this Comet Interceptor mission. I've never heard it before. That's on me. I'm curious if there is interest in the community involved in that mission to talk to the astrophysics community. In particular, the astrophysics part of the community interested in things like transient phenomenon or transits or eclipses. Whether that mission will have the capacity and potential to do time-critical observations.
So if Comet Interceptor can do time-critical observations?
Yeah.
So unfortunately, Comet Interceptor is the first small class mission that ESA is building. So the budget is extremely low for what we're trying to do. So it will be switched off, and there is absolutely no possibility that ESA will allow us to turn it on while it's being parked at L2. And it's mostly human power that is going to be needed to do these observations. And ESA don't want to do operations while we're parked. So unfortunately, no.
That's a pity.